Welcome to the video lecture on Newton's method. Newton's method is a technique for approximating real zeros of a function. It uses tangent lines to approximate the graph of the function near its x-intercepts. Newton's method assumes that a function f is continuous on a to b and differentiable on the interval a to b. If f of a and f of b differ in sign, then by the intermediate value theorem, the only way f can go from a positive to a negative is if it has at least one zero in that interval a to b, and we can approximate it by x equals x sub 1. Now, Newton's method is based on the assumption that the graph of a function f and its tangent line at x sub 1, f of x sub 1 both cross the x-axis at about the same point. Because you can easily calculate the x-intercept for this tangent line, you can use it as a second, better estimate for the zero of f. And this process gets repeated for as many iterations as needed to reach a certain degree of accuracy. So let's draw a picture to visualize what's going on. What we have is just a function that we know starts either positive and goes negative or vice versa, doesn't really matter. But at some point between this a and this b, it obviously hits the x-axis because it's continuous, and by the intermediate value theorem it has to cross that x-axis. Now what we're trying to do with Newton's method is find out exactly where it hits this x-axis, and we'll call this root c. So we're trying to find the location of c. So what we're going to do is we're going to make a guess, and we're going to pick some x value that we think might be a reasonable guess for what that root is. So say that I let x, my first guess, be x sub 1, and that would be this point up here. So this would be x sub 1, f of x sub 1. So the idea behind Newton's method is that if you draw in the tangent line at this point, x sub 1, f of x sub 1, the zero of your tangent line, so where that tangent line crosses the x-axis, which would be right here, should be close to the zero of the function, since a tangent line and a function are acting very similarly when you're close to the point in question. So you can see from this graph that that is true. We got closer to our root by using that tangent line. And so what we would say then is this zero of the tangent line is now going to be called x sub 2, and that becomes my next guess. So then I repeat this process, and I go to my function at x sub 2, which would be this dot, and I would then draw in my tangent line, and where it crosses the x-axis, right here, is now my x sub 3. And ideally, if this process is going to work, these x values are going to get closer and closer and closer to c until I get a very good approximation to what that root is. Okay? So what we're going to do is sort of derive a formula for what this process is requiring us to do. And then we'll be able to use a formula to apply Newton's method instead of having to draw these pictures every time. So let's start with our first guess, that x sub 1, f of x sub 1. We know that the slope of the tangent line at that point would be the derivative at x sub 1. So the slope of the tangent line is f prime of x sub 1. So what would be the equation of the tangent line at x sub 1, f of x sub 1? So what's the equation of this blue line, essentially? Well, we know it goes through this point, and we know it has this slope. This is the m. So I have a point and I have a slope, so I can use point-slope form. So that would be y minus the y-coordinate of our point, which is that f of x sub 1, equals the slope, which is this derivative, times x minus the x-coordinate, which is x sub 1. Now if we were to solve this for y, I could just add this f of x sub 1 over to the other side. So that gives me y equals f prime of x sub 1 times x minus x sub 1 plus f of x sub 1. Now, what did we want to do with this blue line? We were using this blue tangent line to get our next guess, this x sub 2. And this x sub 2 represented the x-intercept of that blue line, where that line hit the x-axis. And how do you find an x-intercept? You let the y value be 0. So to find the x-intercept of this tangent line, we're going to let the y-coordinate over here be 0, and then we're going to solve this for what x should be. So let's substitute in 0 for that y. And what I'm trying to do is figure out what this x value is. You want to solve for x. So I'm going to go ahead and subtract that f of x sub 1 back over to the other side. And if I want to get at this x, I need to get rid of this f prime. So either I could distribute it across, which is fine, or what I'm going to do is actually just go ahead and divide by it right away. So I'll be left with negative f of x sub 1 over f prime of x sub 1, and that is now equal to the x minus x sub 1. So to finish solving for x, I could just add that x sub 1 over to the other side, and that gives me x sub 1 minus f of x sub 1 over f prime of x sub 1, and that is our x by itself. So once I have x solved for, this now became my new x-intercept right here, became my new guess. So I called it x sub 2. So we're going to call this now x sub 2. Now if you repeat this process, then x sub 3 would look very similar, but now we would be using x sub 2 minus f of x sub 2 over f prime of x sub 2. X sub 4 would be using the guess x sub 3 in this formula. And similarly, in general, x sub n plus 1 is going to use the x sub n guess, the guess prior to it, into this formula. So this is our formula for Newton's method. To get the next guess, you take the prior guess, plug it in, take that x value, that guess, minus f at that x value over f prime at that x value. Okay, so here's Newton's method spelled out. Newton's method for approximating the zeros of a function. Let f of c equal to 0, where f is differentiable on an open interval containing c. Then to approximate this 0, to approximate c, we're going to use the following steps. First, we're going to make an initial estimate x sub 1 that is close to c. And sometimes I draw a graph or I use my calculator to get a good guess as to what I think that first initial guess should be. Determine the next approximation by using this formula. So once we've picked x sub 1, to get x sub 2 over here, we would use x sub 1 right here minus f of x sub 1 minus f prime of x sub 1. Okay? If the absolute value of x sub n minus x sub n plus 1, so in other words, the distance between your two guesses is, if that is within the desired accuracy that you're looking for, then you're done. You'll have your answer. Otherwise, we're going to return to step 2 and calculate a new approximation. So once we figure out what x sub 2 is, then we'll use x sub 2 here, here, and here to get x sub 3, and so forth. And we'll continue this process until we get the desired accuracy that the problem asks for. Each successive application of this procedure is called an iteration. So you may need to do 2 or 3 or 4 iterations until you get the accuracy that you're looking for. All right, so let's try an example. We have to calculate 3 iterations of Newton's method for the function 2x squared minus 3 using x sub 1 equals to 1. So this one is actually telling us what our first guess should be. And that's not always the case. We'll try some later where you have to make that first guess. So the important formula that we're going to be using is Newton's method's formula, which is x sub n plus 1. So the next guess comes from x sub n minus f of x sub n over f prime of x sub n. Now, you can see in this formula that we need to know something about the derivative. So let's go ahead and calculate what that derivative f prime of x would be. And we're just going to use our power rule here. The derivative of 2x squared would be 4x, and the 3 goes to 0. So what I'm going to do is substitute in some formulas for what f of x sub n would look like and f prime of x sub n. So this is going to stay x sub n, but the formula for f says I would take 2 times whatever this guess is squared minus 3. So this numerator would be 2 x sub n squared minus 3 over, and then for our derivative we're just going to take x sub n and multiply it by 4, since that's the rule for f prime. So this would be 4 times x sub n. So this is essentially the formula that we're going to be plugging into. So let's make a little table here. Our x sub 1 is going to be that first guess 1, and they told me what to use there. So x sub 2, according to this formula, I'm going to take x sub 1 and put that here, here, and here. So x sub 1 was 1, so I want to put a 1 here, a 1 here, and a 1 here. So it would look like 1 minus 2 times 1 squared minus 3 over 4 times 1. So this would become 1 minus 2 times 1 squared is still a 2. 2 minus 3 is a negative 1. And 4 times 1 is 4. Minus minus becomes plus. So this is 1 1/4, which is 1.25. I'm just going to go ahead and use decimals. Now, to get x sub 3, we're going to do this same process again, but we're now going to be using 1.25 right here, here, and here. So this would become 1.25 minus 2 times 1.25 squared minus 3 over 4 times 1.25. Now at this point the decimals are going to get a little too messy for us to do by hand. So what we're going to want to do is pull out the calculator, and I'm just going to go ahead and type this all in to my calculator. But because this is a fraction over here, you want to be a little bit careful. When we type this into the calculator, we want to make sure that we use parentheses around the numerator and parentheses around the denominator, so that we're making sure to divide all of this top by both of these things in the bottom. Okay, so let's go ahead and pull up the calculator. So what I want to be typing in here is 1.25 minus parentheses 2 times, or 2 parentheses, 1.25 squared minus 3. That was all of my numerator, so I want to close all of that numerator in parentheses, and then I want to divide that by my denominator, which was that 4 times 1.25. And then close the parentheses for that denominator. So when I hit enter, this becomes my next guess. Okay? So that is what this becomes, 1.225. So far I've used this twice. Let's do it one more time. So I'm now going to be using 1.225 for my x sub n. So this will be 1.225 times 2 times 1.225 squared minus 3, all in parentheses, divided by 4 times 1.225. Now an easy way to handle this on your calculator is to just go ahead and use this last command that we just typed in, but change all the 1.25s to 1.225s. So the easy way to do that is to use this entry command in blue right above the enter key. So if I do second enter, it just pastes back in that last command that I had. And what I want to do is change these 1.25s to my last answer. So what I'm going to do is I'm just going to go right on top of them, and I'm going to click on the ANS command, which is right up here above that little negative. So if I do second negative, you'll see that ANS show up, and I'm just going to delete these other things. And now I'm going to go up, and anywhere where I had 1.25 before, I'm going to go on top of it, and I'm going to replace it by that ANS. And that ANS is that 1.225, the last answer that we just computed. Okay, so it should look just like we had typed in before, but now I'm going to be referring to this number as my input. So if we go ahead and hit enter, then this is now our last answer, our next guess, so 1.2247. Okay. Now it doesn't say on this particular example to what degree of accuracy to use, because it just has to do this with 3 iterations. So we did 1, 2, 3 iterations. So I'm just going to stop right here and leave that as my final answer. Most of the time on these problems they will tell you what degree of accuracy they're looking for. So let's see one like that. Okay. Approximate the zero of the function f of x equals x minus 3 plus ln of x. Continue the iterations until 2 successive approximations differ by less than 0.001. So again, the first thing we're going to want to do is use this Newton's method formula. X sub n plus 1 equals x sub n minus the function at x sub n divided by the derivative at x sub n. So let's go ahead and figure out what this derivative needs to be. Derivative of x is 1, derivative of minus 3 goes to 0, plus the derivative of ln of x, and that just goes to 1 over x. So our formula is going to become x sub n plus 1 equals x sub n minus our function, so all of this with x sub n plugged in. And then on the bottom, our derivative, which is this, with x sub n plugged in. Okay, so that's essentially what we're going to be using. Now we want to approximate this 0 so that 2 successive approximations differ by less than 0.001. So I'll show you what that means. We're basically looking for accuracy up until that 3rd decimal position. So once that 3rd decimal position stops changing, then we can stop and give our answer up to that degree of accuracy. Now it doesn't tell me what to use for my very first x sub 1. So this is where a graph comes in handy. So if we pull up the calculator, and in y equals, I have my function typed in. I'm just going to go ahead and graph it in a standard window. And all I'm using this graph for is to get a good guess. We can see that the intercept is right here, and it looks like it's somewhere between 2 and 3. So you can pick your x sub 1 to be anything at all, but to make this Newton's method process go faster, so that you don't have to compute as many iterations, I would always recommend trying to pick a relatively simple guess that's close to where you think that 0 is. So I obviously wouldn't want to start with an x sub 1 of 99. I'd rather start with an x sub 1 of 2, since I know the answer is close to 2. So we're going to just go ahead and use x sub 1 equal to 2 for our first guess. And if I do that, then that means in this formula, x sub 2 would be 2 for right here, minus parentheses 2 minus 3 plus ln of 2, so that's just with this 2 plugged in for that x sub n, over 1 plus 1 over 2. And I'm going to go ahead and type that into my calculator. So I'll go back to my home screen. Let me go ahead and clear some of this stuff out. And what we want is that first guess 2 minus parentheses for that numerator, and we wanted 2 minus 3 plus ln of 2. Close the parentheses on the ln, close the parentheses on the numerator, divided by the denominator, which was our derivative, and that derivative was 1 plus 1 over x, and our x is 2. Close the parentheses on that denominator. So when I hit enter, here is my second guess 2.20456. So let's go ahead and write that down. You can write as many decimals there as you want. We're going to now use that answer as our next guess. So this would be 2.204568 minus 2.204568 minus 3 plus ln of all of that big number. And then all of that divided by 1 plus 1 over. Okay? And then here's where we're going to use our calculator to help us out. I'm going to go ahead and use second entry, and I'm going to scroll back and change all of these 2's to that A and S so that I don't have to waste my time typing in all of those decimals. I'm going to make the calculator use it in this stored A and S button. So change all of these 2's to last answer. And when I hit enter, this is now my next value. So 2.207939. Now you can see that so far this third decimal position here was a 4. This third decimal position here was a 7. So we're still changing, so that means we need to do this again. So our x sub 4 is just going to use this x sub 3. I'm not going to go ahead and bother writing it all out, but we'll be using that x sub 3. And the nice thing is once you've changed that A and S in all of your positions, then your calculator can do this very, very easily. All I have to do is hit second enter, and the A and S now that it's going to refer to is always the very last answer it got. So now it's going to replace this A and S with this 2.207939. I don't have to bother making any modifications at all. I'm just going to go ahead and hit enter, and this automatically gives me my x sub 4. So this is 2.2079400032. Okay, and this is when we know we're done, because if we look at that third decimal position, it is exactly the same as x sub 3's third decimal position, and in fact the 9's match as well. So I know that using Newton's method guarantees that my 0 is going to have accuracy up until that 7 as well as up to that 9, since that didn't change as well. So my approximation would be that this 0C has to be 2.2079 since those all matched. After the 9, it continues to change, so I don't know what that rest of that accuracy would be, but this is more than sufficient. So here would be my final answer. Now, just a note here, when the approximations approach a limit, the sequence of these guesses, the x sub 1, the x sub 2, the x sub 3, the x sub 4, and so on, we say that if that is approaching a number, that's said to converge. And if that limit is c, it can be shown that c must be a zero of this function f. Unfortunately, Newton's method does not always yield a convergent sequence. Suppose that x sub 1 gives a horizontal tangent line. Let's draw a picture to visualize what this might look like. Suppose that you have a function that looks like this. Let me draw that one more time. Okay, and suppose that I happen to pick x sub 1 to be right here, right at that point. What would the tangent line to that graph look like? Well, it's going to be horizontal because our graph is flat right there. And what do you know about the slope of a horizontal line? The slope of a horizontal line is 0, and the slope of this tangent line is the same as the derivative. So since this is horizontal, we know that the derivative at x sub 1 here would be 0. Now remember how Newton's method's formula works. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So if our first guess leads us to a derivative that's 0, then we would be wanting to put a 0 right here in that denominator, and that would cause us to divide by 0. We would have something over 0 right there, and that's undefined. So that means that we're not going to be able to get another guess. We're not going to be able to figure out what x sub 2 is because this formula fails at this particular x sub 1 value. Okay? So sometimes Newton's method will fail. You can see that this wouldn't work because what we're trying to do in Newton's method is use the tangent line to get the x-intercept of that tangent line, and this tangent line never crosses that x-axis. So that's why we're never going to be getting that second guess. So what do you do if something like this happens? If your x sub 1 does yield a horizontal tangent line, then just pick a different value for x sub 1. Try a different x sub 1 instead, and hopefully that will work for you. Okay? All right, let's try another example. We're going to apply Newton's method to the function 2 sine x plus cosine 2x with an x sub 1 equal to 3 pi over 2. So Newton's method says x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So let's find out what our f prime of x is going to be. The derivative of 2 sine x. Well, the 2 will stay there, and the derivative of sine of x is cosine of x. When we go to cosine of 2x, you must use a chain rule. Your outer function is the cosine, and then the inner function is the 2x. So the derivative of the cosine, that wants to be a minus sign. So the derivative of cosine of 2x wants to be minus sine of 2x. But by the chain rule, we have to multiply that by the derivative of this inner function, which is going to give us another 2. So this is going to be 2 cosine x minus 2 sine 2x. So there's our derivative. So that means our formula is going to look like this. X sub n minus parentheses this function with x sub n plugged in, divided by this derivative with x sub n plugged in. Okay? And our first guess, x sub 1, is going to be 3 pi over 2. So x sub 2 would be 3 pi over 2 minus 2 sine of 3 pi over 2 plus cosine of 2 times 3 pi over 2 all over 2 cosine of 3 pi over 2 minus 2 sine of 2 times 3 pi over 2. Okay, so if we take a look at our 3 pi over 2 plugged in, I just want to show you a little bit of this by hand before we pull up our calculator. Think about what cosine of 3 pi over 2 is. That's the same as 270 degrees. It's on the y-axis, so cosine is going to be 0. So this value goes to 0. So then if we look at sine of 2 times 3 pi over 2, the 2's are going to cancel out. And this is just sine of 3 pi, which is the same as 180 degrees on the x-axis, and sine is 0 on the x-axis. So this is also going to be 0. So we're going to be dividing this whole quantity by 0. So this is just like in the last example when we were talking about a horizontal tangent line. This derivative is 0 at 3 pi over 2. So we have a horizontal tangent line at 3 pi over 2, which is bad news for us because it's going to mean that this Newton's method formula doesn't work. It's going to give us something that does not exist. So what we would need to do is revise our initial guess. Instead of using x sub 1 equal to 3 pi over 2, we just need to pick something else instead. So let's just pick any x value that you like. You can pick something close to 3 pi over 2 if you like. Whatever you want will work here. If I try something like just plain old 3, let's see if that's going to work for us. So this formula would then become 3 minus 2 sine of 3 plus cosine of 2 times 3 all over parentheses 2 cosine of 3 minus 2 times sine of 2 times 3. So this is what I want to type into my calculator. Now to save some time, I already punched that in, so you wouldn't have to see me push all the buttons. So we have 3 minus 2 sine of 3 plus cosine of 2 times 3, and then all of that is divided by 2 cosine 3 minus 2 sine of 2 times 3. So if I hit enter, that does give me a legitimate value. So this is a good guess for me. It gets me an actual x sub 2 that works. So my next guess here would be 3.874226372. And now we're going to let x sub 3 be that x sub 2 value minus 2 sine of that x sub 2 plus cosine of 2 times that x sub 2 all over 2 cosine of x sub 2 minus 2 sine of 2 times x sub 2. And I'm just going to use that last entry command to help me get this next guess. So if I do second entry, and I'm just going to go back here and change all these 3's to A and S. Oops. Second. Negative. So they're all going to be replaced by that 3.87 number. Okay, I think I got them all, so I'm going to hit enter, and this now becomes my x sub 3. So 3.519671917. Now to get x sub 4, we would now plug in this x sub 3 value in. I'm not going to go ahead and write out all that formula again, but let's just go ahead and pull up the calculator and type in second entry, hit enter, and it's now going to use that 3.519 number as the ANS. So we get 3.51633. And let's try it one more time here, just so you can see. Whoops, sorry about that. So if I do second entry, hit enter, 3.516327086. All right, now this particular problem did not specify how far to go. I usually, as a rule of thumb, go at least 3 decimal places. So we can see that this 6 and this 6 match, and in fact these 3's match as well. So I can say that my solution, my 0 that I'm looking for with accuracy, is 3.5163, and I wouldn't go any farther than that since I haven't found those decimal places to stagnate and stop changing. So with accuracy, I can verify and say that Newton's method tells me this 0 should be at 3.5163. Okay? All right, let's take a look at one more example here. Apply Newton's method to the function x to the 1/3 with x sub 1 equaling 0.1. So we know that we need x sub n plus 1 equal to x sub n minus f of x sub n over f prime of x sub n. So let's find what f prime of x wants to be. And this would be power rule, bring down the 1/3. And when I subtract 1 from 1/3, I'm going to get negative 2/3. So this formula will become x sub n minus the function would be x sub n to the 1/3, and the derivative would be 1/3 x sub n to the negative 2/3. Now I'm going to go ahead and clean this up a little bit because it's not too hard to do. What we'll see here is that 1 over 1/3 just becomes a 3. You're multiplying by the reciprocal of 1/3, which turns it into a 3 in the numerator. So I'm going to flip this 1/3 up to the top. And then for these x sub n's, because you have an x sub n to the 1/3 over an x sub n to the negative 2/3, by laws of exponents, I'm allowed to subtract those two powers. So 1/3 minus a negative 2/3 just becomes 3/3 or 1. So this becomes 3x sub n to the first. And now that means I have like terms right here. So 1x sub n minus 3x sub n is negative 2x sub n. So it's actually a very simple formula for Newton's method. The next guess is going to be negative 2 times the previous guess. So if we let our x sub 1 be 0.1, then x sub 2 would be negative 2 times 0.1, so negative 0.2. And x sub 3 would be negative 2 times that last answer, so negative 2 times negative 0.2 is positive 0.4. X sub 4 would be negative 2 times that, so that would be negative 0.8. X sub 5 would be negative 2 times that answer, so that's going to be positive 1.6. So take a look at these guesses here that we're getting. Are they approaching a common value? Are they converging? And you can see here that they're not converging. In fact, they're oscillating, going from positive to negative to positive to negative, and they're growing as we do that. So you've got, if you think of a number line here, where here's 0, 0.1 is here, then negative 0.2 is here, and then negative, or 0.4 would be here, negative 0.8 is over here, 1.6 is over here. So you're jumping back and forth across that 0, and each time the next guess is getting further and further away from 0. So they're oscillating and they're not converging. So in a case like this, we would say that Newton's method fails to work. So we're not able to get our 0 based on this. And if you want to look at our function here, you might see why it's failing. Our function was x to the 1/3, and the graph of that's a cube root function. So the graph looks like this. And where is the 0 of this? The 0 is right at the origin. And our first guess was at 0.1. So the problem with this, the reason why this isn't working for us, is think about what the tangent line is doing as we get closer and closer to 0. At 0 itself, the tangent line is actually vertical. So as you get closer and closer to 0, those tangent lines are getting more and more vertical. And what's the slope of a vertical line? It doesn't exist. It goes infinite. And that's why these values here are getting further and further apart, because your derivative, your slope, is getting bigger and bigger and bigger. Okay, so this fails because we have that vertical tangent line happening right where that 0 is supposed to be. So there is a condition that can be shown to be sufficient to produce a convergence of Newton's method to a 0. So this is kind of like a formula that you could use to show that something will converge or not. So in the last problem, we had the function x to the 1/3. Its first derivative was 1/3 x to the negative 2/3. And what we're going to show is based on this formula, and this isn't something I would expect you to memorize, I would just expect you to know how to apply it. If we can show that this function satisfies this inequality, what we would need to show is that the absolute value of the function times the second derivative of the function divided by the first derivative of the function squared, in absolute value that needs to be less than 1 on an open interval containing the 0. If that isn't shown, then your Newton's method will not converge. If this is less than 1, then Newton's method will converge and you'll be able to find your 0. So let's apply this formula to our function from the last example. We know we need f and f prime, but we're also going to need to know what f double prime is. So let's go ahead and find f double prime of x. Using the power rule, that would be this 1/3 stays put, bring down the negative 2/3, and when I subtract 1 from the power, negative 2/3 minus 1, which is the same as 3/3, means the new power is going to be negative 5/3. So this is going to be negative 2/9 x to the negative 5/3 for our second derivative. So let's apply this condition. So according to this, we need to take the function f times the second derivative of f divided by the first derivative of f squared, and in absolute value we want to show that that is less than 1. So our function was x to the 1/3. Our second derivative was negative 2/9 x to the negative 5/3. And in the denominator, the first derivative was 1/3 x to the negative 2/3, and we need that squared. So let's go ahead and simplify this stuff over here. So on the top, we're going to get that negative 2/9, and an x times an x, you're allowed to add those powers. So 1/3 plus negative 5/3 would be negative 4/3. And in the bottom, let's go ahead and square. So we're going to get a 1/9, and when you do a power to a power, you multiply. So negative 2/3 times 2 would be negative 4/3. So these x's actually end up canceling out completely because they're identical, and negative 2/9 divided by 1/9 is the same as negative 2/9 times the reciprocal 9/1. So those 9's are going to cancel, and that means we're left with the absolute value of negative 2, which is just 2. And obviously that is not less than 1. So this shows that Newton's method will not converge. So unless this is less than 1, we won't have a converging sequence, so we won't be able to get our 0 using Newton's method. Okay? All right, on this last page, we're going to see some applications of Newton's method, and we're going to explain why this method fails. So here we have the graph of this cubic polynomial right here, and the first guess is at 3/2, so 1.5. So here's the first guess, and look at what Newton's method is going to do. The tangent line to the graph at that guess would be right along this dashed line coming down. So the 0 of that tangent line is going to hit right at 1. So this x sub 2 would be right at 1. So now we go up to our function, and that is going to result in this point right here. So what would the tangent line look like at that guess? Well, if we draw that, this graph is kind of flat right at the value of 1. So what happens here is that at our second guess of 1, the slope is 0. We get that horizontal tangent line. And that is why Newton's method is going to fail, because remember, in Newton's method, you are always dividing by the derivative in this formula. And if the derivative ever becomes 0 because you have a horizontal tangent line, then that means you're going to be dividing by 0. So Newton's method fails in this example because we get a horizontal tangent line which causes us to divide by 0. So Newton's method will immediately stop because we won't have another intercept that we will get for our next guess. Okay? So as soon as you hit a horizontal tangent line, you're stuck. All right? Let's see what happens or what goes wrong in the next example. So here's another cubic function. This time our first guess is at 2, which is right here. So here's my first guess. If I follow the tangent line down to where it's going to hit the x-axis, that gives me my second guess, x sub 2. So then I go up to my function to see what point I'm looking at, and I look at that tangent line. Well, that tangent line leads me down to this intercept, which is right back to x sub 1. So then I go up to x sub 1, follow its tangent line down again, I'm back to x sub 2, then I go up, I'm back to x sub 1, and so forth. So if you were to write out what this sequence would look like, we would have x sub 1 for our first guess, then x sub 2 would be the second guess, and then we're back to x sub 1, back to x sub 2, back to x sub 1, and so forth. So this sequence alternates between x sub 1 and x sub 2. And obviously that's not going to converge to a 0. So this does not converge. So that's why Newton's method fails. Okay? And the actual 0 is probably going to be somewhere way over here past that 3. So to make it work, you'd probably need to pick an x value closer to where that 0 really is instead of being farther away. Okay? All right, last example. So here's my trig function 2 sine x plus cosine 2x, and here's our 3 pi over 2. So this is actually the example that we did a little while ago. If you look at the graph, we'll see why we had problems here. At 3 pi over 2, that is this point right down here on the graph. And immediately we would want to look at that tangent line, and you can see that this is that minimum value. So there's a horizontal tangent line right at 3 pi over 2. So the slope at our first guess of 3 pi over 2 is 0 because we have a horizontal tangent line. And that means our Newton's method will fail because we're trying to divide by 0. Okay, so what we did is we revised our guess, and instead we picked a different x value at 3, which is somewhere close to where this guy ended up being. So we just picked a different x at 3, and that got us closer to finding that actual 0. So just by changing our first guess, we were able to make this work. All right, that concludes our lecture on Newton's method. Good luck.